In this video, we will introduce our recent work, Learning Event-Guided High Dynamic Range Video Reconstruction. Limited by the trade-off between frame rate and exposure time when capturing moving scenes, frame-based HDR video reconstruction suffers from scene-dependent exposure ratio balancing and ghosting artifacts. Event cameras provide an alternative visual representation with a much higher dynamic range free from the above issues, which can be effective guidance for HDR imaging from LDR videos. However, integrating events with LDR video is challenging due to their inconsistency. In this paper, we propose a multimodal learning framework which consists of three parts: multimodal alignment, confidence-guided fusion, and temporal context encoding. Experiments show that the proposed method demonstrates state-of-the-art performance for both synthetic and real data. The dynamic range of the real words span a wide range of light level. Scenes with a large range of light levels cannot be captured together in a single image, which implies that the dynamic range covered by a single image is limited. There are works handling high dynamic range imaging from the following four perspectives. However, each has its limitations. Merging multiple LDR images may suffer from the misalignment of LDR frames, result in ghosting artifacts, and bring flickering effects. Inverse tone mapping doesn't have reliable HDR information, which cannot reflect the real scenes. Events-only reconstruction has no reliable color information and cannot produce real color images. Existing event-guided reconstruction heavily relies on event reconstruction methods. Let's replot the pipeline of it. It introduces artifacts from reconstructed intensity images. Let's consider the event-guided reconstruction, which has events and LDR frames as the input, and output the HDR frames. However, events and frames have such different expressions, which is the main challenge of reconstruction. Consider different information provided by events and LDR images. Events provide HDR information, while LDR frames provide reliable scene information such as color and contrast in a limited dynamic range. HDR frames are supposed to have reliable HDR scene information. Both events and LDR frames shared the same scene, providing different representations of scene information. In this paper, we propose to perform implicit fusion by an encoder-decoder network, learning to represent events and LDR frames in a shared latent space by two modality-specific encoders, and then integrating them by a fusion module in the bottleneck layer. The shared representation space should well express common and complementary information from events and LDR frames. Thus, we propose to perform intermodality reconstruction from events at first, then fix the decoder and perform the intramodality reconstruction from LDR frames to obtain the modality-specific encoder. Although events and LDR frames are projected into the shared latent space, they have different confidence in different parts of the images. We propose the confidence-guided multimodal fusion to leverage the advantages of two different representations. We introduce the manually designed confidence at first to emphasize more reliable regions and increase the robustness to inherent noise in data, and cooperate with learnable channel-wise attention for weighting the intermediate representation along two separate dimensions, spatial and channel. Along with the encoder-decoder architecture, we obtain the following pipeline. However, due to inconsistent textures among consecutive event stacks and varying exposure of consecutive frames, it's obviously to be flickering. In order to alleviate the flickering artifacts, we introduce the temporal context encoding to utilize the temporal redundant information to suppress the flickering effects and reduce noise in both input modalities. Then we obtain the complete pipeline of the proposed HDR EveNet. In order to show the performance of the proposed HDR EveNet, we build a hybrid camera system to capture real data. The quantitative evaluation results are shown below. Lead-all only provides nonlinear results, which cannot be used to calculate HDR VDP and HDR VQM. The proposed methods achieve state-of-the-art performance on 4 of the 5 metrics, especially HDR VDP, which reflects the ability of HDR information recovery most and has a comparable result on the reminding metric. We also show the qualitative evaluation results on synthetic and real data. The first is the results on synthetic data. In over-underexposed regions of the LDR input, most of the details have been lost while events preserve the HDR information, especially the cloud. The proposed method effectively fuses the two modalities and recovers the lost details. Hain et al. Converted events to intensity explicitly, which leads to stripe-like artifacts. Lau et al. Is a single image-based method that cannot recover missed HDR information. E2V produces severe artifacts in distorted color. Li et al. Heavily depend on the selected exposure ratio. But even with the optimal exposure ratio, the results of Li et al. Present insufficient details on the stones. The next is the results on real data. LDR frame has no texture on the floor and severe noise in the dark. Events provide the texture on the floor, but less information in the dark. The proposed method can recover the floor texture and reduce noise. Han et al. Cannot recover clear texture and suffer from severe noise in the dark. Lau et al. Cannot recover texture on the floor. V2V cannot reconstruct texture in the dark. The result of ESL-net has texture mismatching with LDR. We also show the video on both synthetic and real data. The proposed method can recover higher dynamic range and more consistent videos. In conclusion, we propose to solve the event-guided HDR video reconstruction by following 3 strategies: multimodal alignment, confidence-guided fusion, and temporal context encoding, and demonstrate state-of-the-art performance. Thank you for listening. More information is provided on our project page and lab page.